This video contains the solutions for 14 through 17, your Physics C Mechanics practice test number 2. Number 14, we have a spacecraft orbiting Earth in a circular orbit of radius r, as shown here. Sorry, going this way. When the spacecraft is at position P, a short burst of the ship's engines results in a small increase in its speed. The new orbit is best shown by the solid curve in which of the following diagrams? Well, it can't jump from one orbit to another one. Electrons do that, right? The quantum level, we have weird jumps in energy states, but actual large physical objects can't jump from one orbit to another like that. So that's not going to happen, and that's not going to happen. That would be jumping out, so those are not options. And if you remember what Kepler's first law says, it says that orbits are elliptical and that the central object, the sun or the Earth, if you have a moon orbiting or whatever, or in this case the Earth with a satellite going around, that central object has to be at one of the focal points of the ellipse. So E, you have the Earth at the center of an ellipse, and that actually doesn't happen, right? We either are at this focus or this focus of that ellipse. So these are the two possibilities. So a burst of speed, is that going to send you further away or closer? Different ways to understand that. If you have a burst of speed, that's going to increase the kinetic energy of the system, and that means that at the other side here, we're going to be further away from the planet, and that will give us more potential energy, more gravitational potential energy. We know that it's going to slow down over here on this side here, and the conservation of angular momentum is also key in understanding this. And if we had actually numbers to work with, remember from your last practice test that the conservation of angular momentum helps us actually figure out velocities at these points. Also here, you know that if you have an extra boost, you remember when you played around with your with the iPad lab doing gravitation stuff, if something's going too fast, then it tends to just go off and not circle around. If it's going too fast, it doesn't come into a tighter orbit. It just doesn't go into orbit at all, or goes into a very large elliptical orbit, or in this case, an elliptical orbit that's bigger than the circular one. So the correct answer is D. Number 15, student holds one end of a string in a fixed position. A ball of mass 0.2 kilograms is attached to the other end of the string and moves in a horizontal circle of radius 0.5 meters with a constant speed of 5 meters per second. How much work is done on the ball by the string during each revolution? Well, there's more than one way to understand that. One easy trick, I guess, is to say that in one revolution, the ball goes from here to here again. So its displacement is 0. So if you're thinking about work as force times distance, the distance is 0, so that gives us 0. That is the right answer. But I think better to understand it this way. Work is equal to the change in kinetic energy. Now, this thing is going at a constant speed of 5 meters per second. Its direction is always changing. But kinetic energy, or any kind of energy does not have direction. So if this thing's going around the circle like this, its kinetic energy is 1/2 mv squared. And it's the same because it's going at 5 meters per second all the time. So if its kinetic energy is not changing, there's no work being done on it. So the correct answer is A. This is, I think, the correct way to understand that problem. Number 16, a wheel of 1/2 meter radius rolls without slipping on a horizontal surface. The axle of the wheel advances at a constant velocity, moving a distance of 20 meters in 5 seconds. So that's its V. 20 meters in 5 seconds would be 4 meters per second. The angular speed of the wheel about its point of contact, let's see, angular speed is equal to v times r, so that would be v times r, and r is, oh sorry, v divided by r. And you can catch, if you look at the units here, I caught myself actually because of the units. We want the meters to cancel out, and we want to have per second, radians per second, so 4 divided by 0.5 is C, 8 radians per second. Number 17, let's see if we can figure this out. We have a long board is free to slide on a sheet of frictionless ice. As shown in the top view above, a skater skates to the board and hops onto one end, causing the board to slide and also rotate. In this situation, which of the following occurs? Well, let's just try to imagine what's going to happen there. Once the skater hops on, the center of mass of the system might be, I don't know, somewhere around here. Be closer to this end if the board were uniformly distributed. And the whole system with the skater is going to rotate around the center of mass. Right? Remember when you throw something, spin it across the room, some oddly shaped object, like a board with a skater attached to it, it will rotate about its center of mass. So as this slides along, the center of mass will just move in a straight line, right? There's no force after that. And it will rotate around that too because of the torque, the force applied at some distance from that center of mass. So let's see. Linear momentum is converted to angular momentum. Can that ever happen? Well, I mean, it's kind of happening here, but there's really some linear momentum left. So I think maybe a better description, like when a kid comes and, remember this test problem, when a kid comes and jumps onto the edge of a merry-go-round type thing, and this thing can't move, it can only rotate. Then we have linear momentum turning into angular momentum. So in this case, I think we still have linear momentum left over. So how about kinetic energy is converted to angular? Well, energy can't be turned into momentum. Energy turns into other kinds of energy, so that doesn't make sense. Rotational kinetic energy is conserved. Well, how much rotational kinetic energy is there before? I would say 0, right? We have the skater who's just going in a straight line and the board that's not rotating. So at the beginning we have none, and then afterwards the board rotates, so we have some, so it's not conserved. How about translational kinetic energy? Is that conserved? Well, we've got skater skating along, and then the board here, the center of the board, moves along like this. And in a collision where two things stick together, translational kinetic energy is typically not conserved, so that's not correct. Let's hope this one is. Linear momentum and angular momentum are both conserved. That's actually true. Linear momentum is conserved because this can move. It's not conserved here in this kind of situation because we go from having linear momentum to not having any, because then the kid sticks here, it only rotates. But here, this does, because it's on a frictionless surface, it does keep moving, and momentum will be conserved. And it will also rotate around that. So both linear momentum and angular momentum are conserved. That's correct. And let me just say one more thing about that. You might say, well, wait a minute, does this have any angular momentum at the beginning? And we say, yes, it does. At the instant the skater jumps on here, we measure his or her rotational or angular momentum around the center of mass of the system, right? Whatever point it's going to start rotating around. So that's just our L equals R cross P, right? And that would be just R times P because it would be a 90-degree angle there.